Welcome! In this session, we'll explore the problem titled Minimum Absolute Difference Queries. We'll break it down step by step, examine different approaches, and learn how to solve it efficiently. Let's dive in. In this problem, we are given an integer array called nums and a 2D array called queries. Each query specifies a range within the nums array, defined by indices L_i and R_i. Our goal is to determine the minimum absolute difference between any two elements in the subarray defined by those indices for each query. If the subarray contains fewer than two elements, we return -1 as the result for that query. The input includes two main components: nums, which is a one-indexed integer array of size up to 10,000, where each value ranges between 1 and 100, and queries, which is a 2D array of up to 20,000 queries. Each query specifies a range within nums that satisfies the constraints 1 equals L_i equals R_i equals n. The output is an array answer of size m, where each element corresponds to the result of a query. Let's explore an example to better understand the problem. Suppose nums is 1, 3, 4, 8, and queries contains the ranges 0, 1, 1, 2, 0, 3. For the first query, the subarray is 1, 3, and the absolute difference between the two elements is 1, 3 equals 2. So, the result for this query is 2. For the second query, the subarray is 3, 4, and the absolute difference is 3, 4 equals 1. The result for this query is 1. For the third query, the subarray is 1, 3, 4, 8. The absolute differences between consecutive elements are 1, 3 equals 2, 3, 4 equals 1, and 4, 8 equals 4. The minimum among these is 1, so the result for this query is also 1. The output for this example is 2, 1, 1. Now, consider another example where nums is 4, 2, 1, 10, and queries contains the ranges 0, 2, 1, 3, 0, 3. For the first query, the subarray is 4, 2, 1. The absolute differences are 4, 2 equals 2 and 2, 1 equals 1, so the minimum is 1. For the second query, the subarray is 2, 1, 10. The absolute differences are 2, 1 equals 1 and 1 to 10 equals 9, and the minimum is again 1. For the third query, the subarray is 4, 2, 1, 10. The absolute differences are 4, 2 equals 2, 2, 1 equals 1, and 1 to 10 equals 9. The smallest value here is 1. Hence, the output for this example is 1, 1, 1. Finally, let's look at a case where there is only one element in the subarray. If nums is 10, and the query specifies the range 0, 0, the subarray is 10. Since there is only one element, there are no pairs to calculate absolute differences, so the result for this query is -1. The constraints of the problem ensure that the solution must handle edge cases like this gracefully. Additionally, the constraints require the solution to be efficient even for large inputs, where nums has up to 10,000 elements and queries contains up to 20,000 ranges. Edge cases to consider include subarrays with a single element, where the result is always -1, subarrays where all elements are identical, resulting in a minimum difference of 0, and scenarios with large input sizes, where optimization is key to meeting performance requirements. To solve the minimum absolute difference queries problem, we first consider the brute force approach. In this method, for each query, we extract the relevant subarray from the list, sort it, and calculate the minimum absolute difference by comparing adjacent elements in the sorted subarray. While this approach is straightforward and guarantees the correct result, it is computationally expensive. Extracting and sorting the subarray takes k log k, where k is the size of the subarray. When repeated for multiple queries, the total time complexity grows to q*n log n, where n is the maximum subarray length and q is the number of queries. This makes the brute force approach infeasible for large inputs, especially when n can go up to 100,000. The main drawback here is the repeated sorting, which is redundant and inefficient. On the other hand, it is easy to implement, making it a good starting point for understanding the problem. To overcome these inefficiencies, we turn to an optimized approach that avoids redundant sorting by pre-computing key information. The optimized approach utilizes a concept called prefix frequency arrays to make query processing more efficient. The first step is to pre-compute a frequency array. This array, frequency, keeps track of how many times each number appears in the list from the startup to any given index. Using this prefix frequency array, we can compute the frequency of any number within a specific subarray in constant time. This is done with the formula, frequency, r plus 1, v, frequency, l, v, where l and r are the boundaries of the subarray. Once we have the frequency information, processing each query involves identifying the distinct numbers in the subarray and their frequencies. These numbers are stored in a sorted list, and the minimum absolute difference is calculated by iterating through adjacent numbers in this sorted range. The complexity of this approach is far more efficient. Pre-computing the prefix array takes O and asterisk max underscore val, where max underscore val is the maximum value in the list, which is capped at 100. For each query, since the number of distinct values is at most 100, processing is limited to O, 100 asterisk q, simplifying the overall complexity to O, n plus q. This makes the optimized approach not only scalable but also well-suited for large inputs. This optimized approach is particularly effective for the constraints of this problem, where the size of the array and the number of queries can go up to 100,000, but the range of values in the array is limited to just 1 to 100. This limited range ensures that even though we use additional memory for the prefix frequency array, the processing of subarrays remains efficient. The trade-off in memory is justified by the significant reduction in computation time, as the pre-computed data eliminates redundant operations like repeatedly sorting subarrays. In summary, the optimized strategy not only addresses the inefficiencies of the brute force method but also scales well with larger inputs. By leveraging pre-computation, we reduce the time complexity of queries and ensure that the solution is both fast and practical for real-world scenarios. The problem we're solving involves a list of integers, nums, and a series of queries. Each query specifies a subarray of nums by providing the indices L underscore I, R underscore I. The goal is to determine the minimum absolute difference, or MAD, between any two adjacent elements in the sorted version of this subarray. To clarify, for a subarray like 8, 2, 4, sorting it results in 2, 4, 8. The differences between adjacent elements are a 4-2 equals 2 and 8-4 equals 4, so the minimum is 2. The challenge lies in optimizing this process, especially when dealing with large arrays and numerous queries. One straightforward way to solve this is using a brute force approach. For each query, you extract the specified subarray using slicing, sort it, and then calculate the MAD by iterating through consecutive elements. Sorting the subarray takes O, k asterisk log k, where k is the size of the subarray, and calculating the MAD takes O, k. If the array nums has a length of n and there are q queries, the overall time complexity can reach O, q asterisk k asterisk log k. While this approach works, it becomes inefficient for large inputs. To address this, we introduce an optimized solution that leverages a segment tree for pre-processing the data. The optimized approach begins with building a segment tree. Each node in the tree represents a range of the array, start, end. Leaf nodes correspond to individual elements of nums, stored as singleton arrays. Internal nodes represent larger ranges, and their values are the sorted arrays of those ranges. To construct the tree, we merge sorted arrays from child nodes using a two-pointer technique, which is efficient and ensures the construction process runs in O, n asterisk log n. When querying the tree, we identify all segments that overlap with the range specified by the query, merge their sorted arrays, and then calculate the MAD from this merged array. Querying a segment tree involves merging arrays in O, log n asterisk k, time, where k is the size of the subarray. Overall, pre-processing takes O, n asterisk log n, and querying is significantly faster compared to the brute force approach. The key to the optimized solution is recognizing that repeatedly sorting subarrays is inefficient. By pre-computing sorted subarrays within a segment tree, we can reuse this data for overlapping ranges. Since the MAD depends only on adjacent elements in the sorted array, the computation becomes linear once the subarray is sorted. The use of a segment tree allows for efficient merging of overlapping segments during queries, making it the ideal data structure for this problem. It's important to consider edge cases, such as subarrays of size 1, where MAD is undefined, or subarrays with duplicate elements, where MAD can be 0. Large inputs are also handled efficiently due to the pre-processing step that reduces redundant computations. When implementing this solution, it's vital to address several edge cases. For single-element subarrays, the mat is undefined, so it's common to return a placeholder value like -1. Subarrays with identical elements result in a mat of 0 since all differences are 0. Queries that span the full array also need to be handled efficiently, as they involve merging multiple segments. Finally, the algorithm must remain performant under constraints involving large array sizes or numerous queries. To illustrate how this works, let's look at an example. Suppose nums equals 4, 2, 8, 6, 7, and we're given the query 1, 3. The subarray extracted is 2, 8, 6, which sorts to 2, 6, 8. The differences between adjacent elements are 4 and 2, so the mat for this query is 2. For the second query, 0, 4, we extract the subarray 4, 2, 8, 6, 7. Sorting this subarray gives 2, 4, 6, 7, 8. The differences between adjacent elements are 2, 2, 1, and 1. The minimum among these is 1, so the mat for this query is 1. Combining the results of the two queries, we get the final output of 2, 1. This example highlights how the segment tree efficiently handles range queries and minimizes redundant computations, providing an optimized solution to the problem. Here, we begin by importing the necessary libraries, defaulted from the Collections module and the Math module for handling mathematical operations. Within the solution class, the min-difference method takes two inputs, the array nums and a list of queries. The goal is to efficiently compute the minimum absolute difference of distinct numbers within specified subarray ranges. To do this, we first calculate the prefix frequency for all numbers in the range 1 to 100, which is the assumed maximum value of elements in nums. This is achieved using a list of defaultics, where prefix_frequency, I, represents the frequency of numbers from the start of nums up to the ith index. By iterating through the array, we populate these frequency dictionaries, ensuring that each prefix_frequency, I, builds upon the previous one. This pre-computation allows us to quickly calculate the frequency of each number within any subarray range, which will be useful for answering queries. Once the prefix frequency is prepared, we initialize an empty list result to store the answers for each query. For every query, which specifies a range, L, R, we calculate the frequency of numbers within this range by subtracting the frequency counts at the boundaries of the prefix array. This gives us the count of each number appearing in the subarray, which we then use to identify the distinct numbers present in the range. These distinct numbers are stored in a list called unique_nums, which is sorted to ensure the numbers are in ascending order. Sorting makes it easier to compute the minimum absolute difference between consecutive elements. We initialize a variable min_diff to positive infinity, which will help us track the smallest difference as we iterate through pairs of adjacent numbers in the sorted list. For each pair, the absolute difference is calculated, and min_diff is updated if a smaller difference is found. Once all pairs are checked, we append the result of this query to the result list. If min_diff remains positive infinity, which happens when there are no distinct numbers in the range, we append -1 to indicate no valid difference exists. Finally, after processing all queries, we return the result list containing the answers for each query. This efficient approach leverages pre-computation and sorting to handle multiple queries while minimizing redundant calculations. Here, we begin by importing the necessary libraries and defining our solution class. The focus of this implementation is to efficiently handle the minimum absolute difference queries problem. We start by defining the function min_difference, which takes an array of integers, nums, and a 2D array of queries as input. First, we calculate the length of the nums array and define a constant maxval as 100, which represents the range of possible numbers in nums, from 1 to 100. To efficiently process the queries, we pre-compute a prefix frequency array, prefix frequency, where each row corresponds to a position in the input array and each column represents the frequency of a specific number up to that position. The outer loop iterates over the elements of nums, while the inner loop updates the frequency counts for all numbers from 1 to 100. For each position I in nums, we copy the frequency counts from the previous position and increment the count for the number at the current index. This pre-processing step ensures that we can quickly retrieve frequency information for any range. Next, we initialize a list called result, which will store the final answers for each query. Then, we iterate over the queries, extracting the range, L, R, for each.
The goal is to calculate the frequency of each number within this range. To do this, we loop through all possible numbers from 1 to 100 and check if their frequency in the range is greater than 0. If so, we add the number to a list called uniquenums, which will store all distinct numbers present in the range. Once we have the list of unique numbers in the range, we proceed to compute the minimum absolute difference between any two consecutive numbers in this list. To achieve this, we initialize a variable mindiff with the maximum possible integer value. We then iterate through the uniquenums list, calculating the difference between consecutive elements and updating mindiff with the smallest difference encountered. This step ensures that we efficiently determine the minimum absolute difference. After computing the minimum difference, we check if the uniquenums list contains more than one number. If it does, we add the computed mindiff to the result list. Otherwise, if there are no valid pairs to calculate a difference, we append -1 to indicate this. Once all queries are processed, the final result list, containing the answers for each query, is returned. This implementation efficiently handles the problem by leveraging prefix frequency arrays for quick range queries and minimizing redundant computations, making it well suited for large input sizes. To solve this problem efficiently, we start by pre-computing the prefix frequency for numbers ranging from 1 to 100. This will allow us to calculate the frequency of any number in a given range without recalculating from scratch. We initialize an empty frequency map for each index of the array, plus one extra for the zero-based prefix. As we iterate through the array, we copy the frequency map from the previous prefix and increment the count for the current number. For example, after processing the first number, the prefix frequency at index 1 contains 1, 1. After processing the second number, we have 1, 1, 3, 1, because both 1 and 3 have been seen once. This process continues, and by the end, the prefix frequencies for all indices are pre-computed. With this setup, we can now process each query efficiently. For a query, L, R, we subtract the prefix frequency at L from the prefix frequency at R plus 1 to get the frequency of numbers in the range, L, R. Now let's process the queries one by one. For the first query, 0, 1, we subtract prefix underscore frequency, 0, from prefix underscore frequency, 2, which gives us the frequency count, 1, 1, 3, 1. The unique numbers in this range are 1, 3. The minimum absolute difference between these numbers is 3, 1 equals 2. For the second query, 1, 3, we subtract prefix underscore frequency, 1, from prefix underscore frequency, 4, resulting in the count, 3, 1, 4, 1, 8, 1. The unique numbers are 3, 4, 8. The minimum absolute difference can be calculated as the smallest difference between consecutive numbers, which is min, 4 to 3, 8 to 4, equals 1. Finally, for the query 0, 3, the frequency count is 1, 1, 3, 1, 4, 1, 8, 1. The unique numbers are 1, 3, 4, 8, and the minimum absolute difference is min, 3 to 1, 4 to 3, 8 to 4, equals 1. The final result for these queries is 2, 1, 1. In this example, the array is 2, 9, 6, 3, and the queries are 0, 2, 1, 3, 2, 2. Similar to before, we start by pre-computing the prefix frequency. At index 1, we encounter the number 2, so the prefix frequency becomes 2, 1. At index 2, we add 9, resulting in 2, 1, 9, 1. At index 3, we include 6, giving 2, 1, 9, 1, 6, 1. Finally, at index 4, we include 3, resulting in 2, 1, 9, 1, 6, 1, 3, 1. With this pre-computation done, we can process the queries. For the first query, 0, 2, we subtract prefix underscore frequency, 0, from prefix underscore frequency, 3, which gives 2, 1, 9, 1, 6, 1. The unique numbers are 2, 6, 9, and the minimum absolute difference is min, 6 to 2, 9 to 6, equals 4. Next, for the query 1, 3, we subtract prefix underscore frequency, 1, from prefix underscore frequency, 4. This gives the frequency count, 9, 1, 6, 1, 3, 1. The unique numbers in this range are 3, 6, 9, and the minimum absolute difference is found as min, 6 to 3, 9 to 6, equals 3. For the query 2, 2, we subtract prefix underscore frequency 2 from prefix underscore frequency 3, resulting in 6, 1.
Since there is only one unique number in this range, the minimum absolute difference is -1, which indicates that the calculation is not possible with just one number.
The final result for these queries is 4, 3, -1.
In this example, the array is 10, 10, 10, and the queries are 0, 2, 1, 2, 0, 0.
As before, we begin by pre-computing the prefix frequencies. At index 1, the frequency is 10, 1. At index 2, we add another 10, resulting in 10, 2. At index 3, we have all three 10s, making the frequency 10, 3. For the first query, 0, 2, we subtract prefix underscore frequency 0 from prefix underscore frequency 3, giving 10, 3.
The unique number in this range is 10, and since there is only one unique number, the minimum absolute difference is -1.
For the query 1, 2, we subtract prefix underscore frequency 1 from prefix underscore frequency 3, resulting in 10, 2.
The unique number in this range is still 10, so the minimum absolute difference remains -1. Finally, for the query 0, 0, we subtract prefix underscore frequency 0 from prefix underscore frequency 1, which gives 10, 1. Again, there is only one unique number, so the minimum absolute difference is -1. The final result for these queries is -1, -1, -1. Here, we analyze the time complexity of the solution by dividing it into two main steps.
The first step is pre-computing the prefix frequency.
In this step, we maintain a prefix frequency dictionary at each index of the array nums. For every index, we copy the dictionary from the previous index, which involves at most 100 keys since the numbers in nums range from 1 to 100. Copying this dictionary takes constant time, specifically 100, and updating the frequency of the current number is an O1 operation. Multiplying this by the number of indices in the array, n, gives us a total time complexity of O(n*(O100), which simplifies to O(n). This step is efficient because the constant factor of 100 does not grow with the size of the input.
The second step involves processing the queries.
For each query, L, R, we calculate the frequency of numbers in the range by subtracting two prefix frequency dictionaries. Since each dictionary contains at most 100 keys, this subtraction operation is O100, which simplifies to O1. After that, we extract the unique numbers in the range by iterating over the numbers from 1 to 100. This is also O100 equals O1. Sorting these unique numbers takes k log k, where k is the number of unique numbers, and since k is at most 100, this operation becomes a constant time step. Finally, calculating the minimum absolute difference involves iterating through the sorted unique numbers, which is k equals 100 equals 1. Therefore, processing a single query has a constant time complexity of 1. For m queries, the total complexity becomes m. Combining the time complexities from both steps, the overall time complexity of the solution is n plus m, where n is the size of nums and m is the number of queries. Now, let's discuss the space complexity of the solution. The primary contributor to the space complexity is the prefix frequency storage. We maintain a prefix frequency dictionary for every index in nums, including one extra for the 0th index, resulting in n plus 1 dictionaries. Each dictionary contains at most 100 keys, so the total space required is O(n*(O100), which simplifies to O(n). During query processing, we use temporary storage to calculate the frequency of numbers in the range L, R, which requires a dictionary with at most 100 keys and a list to store unique numbers. Since this temporary storage is reused for each query and does not scale with the input size, it is O1. Therefore, the overall space complexity is dominated by the prefix frequency storage and simplifies to O(n).
When comparing the optimized solution to the brute force approach, the efficiency becomes clear.
In the brute force method, for every query, L, R, we would extract the subarray nums, L, R plus 1, which takes time proportional to the size of the range, O, R, L plus 1. Sorting this subarray adds another O, R, L plus 1, log, R, L plus 1, and calculating the minimum absolute difference involves one more pass through the subarray, adding O, are L plus 1. For M queries, this results in a total time complexity of O, M, asterisk, O, are L plus 1, plus O, are L plus 1, log, are L plus 1. In the worst case, where the range size is the entire array, this becomes O, M n log n. By contrast, the optimized solution avoids redundant computations by using pre-computed prefix frequencies. This reduces the time complexity to O, n, plus O, m, which is a significant improvement, especially for large inputs. To wrap up, let's analyze the best, average, and worst case complexities. In the best case, where there is only one query, m equals 1, the total complexity is O, n, plus O, 1, which simplifies to O, n. In the average case, the complexity remains O, n, plus O, m, for general inputs. Even in the worst case, with large values for both n and m, the complexity remains O, n, plus O, m, demonstrating that the solution is highly scalable. This efficiency is mathematically justified because the prefix frequency computation scales linearly with the size of the input array n, and query processing scales linearly with the number of queries m. Additionally, steps like sorting and difference calculation are effectively constant due to the bounded range of numbers from 1 to 100. This ensures that the solution's overall time complexity, O, n, plus O, m, is both optimal and robust for large-scale problems. When solving this problem, there are a number of common mistakes to watch out for. First, overlooking edge cases can lead to incorrect results. For example, single-element subarrays, empty queries, or duplicate values in the array might behave differently than expected. Testing your solution with minimal input sizes and edge scenarios can help identify these issues early. Next, relying on an inefficient brute force implementation can cause timeouts, especially when dealing with large constraints like n greater than 10,000. Instead, look for ways to optimize repetitive operations using preprocessing or efficient data structures. Another common issue is incorrect index handling. This typically happens when there's confusion between zero-based and one-based indexing, resulting in incorrect subarray selection. To avoid this, always validate your index ranges with test cases. Additionally, it's important not to ignore constraints like maximum input size or potential for integer overflow. For instance, if input values can exceed 10 to the power of 9, your algorithm must handle large numbers efficiently. Finally, skipping pre-computation opportunities can drastically increase time complexity in problems with multiple queries. Techniques like prefix sums or segment trees can eliminate redundant calculations and make your solution far more efficient. Now, let's talk about some insights that are particularly helpful in an interview setting. First, take the time to fully understand the problem scope. Determine whether you're working with absolute differences, minimum or maximum values, or some other derived metrics, and clarify constraints with your interviewer if needed. Next, be prepared to discuss trade-offs between space and time complexity. For example, pre-processing techniques like prefix sums, sparse tables, or segment trees can significantly reduce query time, but they come at the cost of increased space requirements. It's a good idea to weigh these trade-offs explicitly. Additionally, if the problem involves multiple queries, prioritize methods that pre-process the array to enable constant or logarithmic query times. This shows that you're thinking about scalability. Lastly, always explain your approach clearly. Start by describing a brute force solution, then highlight its inefficiencies before systematically introducing optimizations. This demonstrates your problem-solving process and ensures the interviewer understands your thought process. To deepen your understanding, it's helpful to explore related problems. For instance, LeetCode 209, minimum size subarray sum, focuses on sliding window techniques, which are often useful for subarray problems. LeetCode 325, maximum size subarray sum equals k, introduces the use of prefix sums and hash maps, providing a strong foundation for handling subarray sum problems. LeetCode 53, maximum subarray, is a classic problem that emphasizes the power of dynamic programming for optimizing subarray computations. Finally, LeetCode 1208, get equal substrings within budget, showcases the sliding window approach in scenarios where additional constraints are applied. Studying these problems will not only strengthen your understanding of subarray-based techniques but also prepare you for variations in interview scenarios. For this problem, it's worth considering a range of alternative approaches depending on the input size and constraints. The brute force approach, where you directly iterate through each query and calculate the result, is conceptually simple but highly inefficient for large datasets, with a time complexity of n squared or worse. A more efficient option is using prefix sums, where you pre-compute cumulative sums to allow range queries. While this approach requires n additional space, it significantly reduces the time complexity for queries. Another powerful technique involves data structures like segment trees or Fenwick trees, which are particularly useful for range queries and updates. They provide log n query and update times but come with additional implementation complexity and space requirements. Finally, for problems involving finding minimum or maximum differences, sorting the array can simplify the process. When combined with binary search, this method allows for efficient lookups and can drastically reduce the overall complexity. Each approach has its trade-offs, and the best choice depends on the specific constraints and requirements of the problem. Great job! We've summarized the key approaches and takeaways from solving minimum absolute difference queries. Remember, practice is key to mastering these problems. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!